Today's daily LeetCode problem of the day is minimum number of operations, the sorted binary tree by level, number 2471. For this problem, we're given the root of our binary tree with unique values. In one operation, we could choose any two nodes at the same exact level, and we could swap their values. So, we want to return the minimum number of operations that will be needed to make the values at each level sorted strictly on an increasing order, and the level of a node is the number of edges along the path between it and the root node. So the level of a node is the number of edges, simply meaning however many connections it takes to get to that node. So from 1 to 4, there's one connection. From 4 to 6, there's two connections. So this is level 0, this is level 1, and this is level 2. So similarly, from 1 to 3 is one connection, and from 3 to 8 is a second connection. So we want to sort this entire row together on a strictly increasing order. That would be 5, and then 6, and then 7, and then 8. So 5 would switch with 7, 6 would stay the same, and then 7 would switch with 8. So we would have 5, 6, 7, 8. That's all we have to do for this problem. We could simply solve this by using a breadth first search. So we will tackle the tree row by row. So we'll use our tree traversal. We'll traverse by level, collecting the values at each level, and then we'll use a sorting logic. So for each level, we'll calculate the minimum swaps required to sort the values using a cycle detection in index mapping. We'll go through that. And finally, we'll sum up all the swaps across all the levels. So first thing we want to do in our main function is identify how we're going to traverse the tree. So we're going to use a breadth first search, which is going to require us to use a queue, and we're going to store the values of all the levels on, or all the nodes on one level in that queue for us to traverse. So because this is going to be a recursive function, we will first identify our break, or our base case. So if our root is ever equal to null, meaning that we are out of nodes to traverse, we can return 0, as we don't need any changes. Now we're going to implement our queue. This queue is going to store all the nodes that we're going to traverse at that level. So we're going to have a queue. It's going to store tree nodes, and we could call it our queue, and it's a new linked list. So with this queue, we're first going to add our root, as that is the first initial node that we are going to look for its children, and then we'll identify how many operations this is going to take. So while our queue is not empty, while it's not empty, we are going to get the level size, meaning however many elements are in the queue. So we'll store that, and that's how many elements we're going to have to traverse. And we will collect all their children and add them to the queue as well. So sorry, it's going to be level size is equal to queue.size. And then we'll have an integer array called level, and this is going to be of length level size. And this will simply allow us to put all of the elements in order based off how they originally start, and then we'll calculate how many moves we're going to need to make to sort them. So we'll first collect those values from our current levels. So for each integer I is equal to 0, as long as I is less than our level size, I will increment, and we will take whatever node is at the top of the queue. So tree node temp is going to be equal to queue.pull, and we will equal level of I equal to that temporary value. So using that, we can first figure out how much that's worth, and then we will traverse its children, but we will also be able to sort this level array to calculate how many swaps are needed. So now that we've updated our level array, we will add the current temp nodes left and right child to our queue. So if node.left is not equal to null, meaning that that tree node exists, then we can queue.add node.left. Same thing for right. So if node.right is not equal to null, then q.add our node. Sorry, this is our temp left, temp right, and we will add our temp left and our temp.right. And that's it. So that is going to first put all the values into their respect positions on each level, and then we will add their children to the queue so we can traverse them in the future. And then we will calculate how many operations it will take to sort that level array. So we'll do this by equaling our operations plus equaling, and we'll call to a helper function called our min swap to sort, and we will pass it our level array so we can calculate how many swaps are needed. Then we can simply return our operations. Now, for this helper function. This helper function is going to use a technique involving a cycle detection, and it ensures that we're going to minimize the swaps by detecting and resolving misplaced elements efficiently. So we can go ahead and begin to define our new function. So our function, we can make it a public. It's going to return an integer, and it's called min swap to sort. And it's going to receive an integer array called level, but we could call it our ARR. So in this function, we are going to take all the elements and simply sort them, but we need to calculate how many moves it's going to take to sort them. And we can only swap 2 elements at a time. So we'll first identify the length. So int n is equal to our ARR.length. And we're going to create a 2D integer array called our indexed ARR. And this is going to help us keep track of how many moves we need to make. Now we're going to pair the values with their original indices in our indexed ARR so we can compare it to the final result. So for each integer I is equal to 0, as long as I is less than n, I can increment. So indexed ARR of I of 0 is going to be equal to the ARR of I, so the value, and then indexed ARR of I of 1 is simply going to be equal to I to keep track of the initial index. Now we can sort our array by the values, keeping track of their original indices, so we can calculate how many moves it would take to reach that. So arrays.sort our indexed ARR, and then we're going to use a lambda function to define how we want to sort it because it is a 2D array. So we're going to take an element A from the array and an element B from the array, and we're going to use a lambda function to integer.compare A of 0 to B of 0. So we're going to sort them on an increasing order. And this is simply defining how we're going to sort that function. Next thing we're going to do is identify a Boolean array called visited. And that's going to keep track of the nodes that we visited. So new Boolean of n. And we're going to call a integer called swaps. So we can begin to track how many swaps it takes to reach our end goal. So we're going to detect and count cycles in our index mapping. Basically just going through and identifying the swaps needed to reach indexed array's sorted state. So for each integer I is equal to 0 again, I is less than n, I can increment. And if our visited of I is, if visited of I or our indexed array of I of 1 is equal to I, we can continue, meaning that it stayed in the same place. Otherwise, we will create an integer called our cycle size. This is how many moves it's going to take, and an integer j is going to be equal to I. This is going to be our second indice. So while not visited of j, so while we're not at that element, visited of j will equal to true unless otherwise decided. So j is going to be equal to indexed ARR of j of 1. So we're going to update that indexed array, basically equating j to that, and as long as that is not true, as long as j is not in the right spot, we will continue to try and put it in the right spot. And then we can increase our cycle size by however many moves that is going to end up taking. And then each cycle of size k will actually be equal to k minus 1 because it's a 0 indexed array. So as long as our cycle size is greater than 1, then we can say our swaps will plus equal cycle size minus 1 since it's 0 indexed. And then we can return our swaps. And that is it for this problem. So basically, here's our performance breakdown. We're going to traverse our tree, which takes O of n time. We're going to sort each level in our helper function, which is O of k log k, where k is the number of nodes at each level. And overall, it should take O of n log k time, where k is the average number of nodes per level. So if we run this, passes our test cases, and if we submit it, passes all solutions. Thank you, and follow for more daily LeetCode solutions.